Okay, so let's quickly go over the exam. First problem, so this is exam 1 review. The first problem says, and I'm going to be going through this quickly, so I'm going to be abbreviating the problem. Convert this to radians. Okay, so we're converting this to radians. Find the radian measure of this angle. Okay, so we know to convert to radians, we're just going to use that little formula that says we multiply by 180 degrees. Sorry, got that backwards, thinking it, by pi over 180 degrees. So the degrees cancel and we're left with an angle measured in radians. And I'm not going to actually calculate, well actually I can because I can see the answer there. You plug this into your calculator, get an approximation, and I'm getting 0.401 radians. Okay, radians. Okay, the next problem is similar. It says convert -3 pi on 2 to degrees. So we're converting to degrees. So we'll do the opposite. We'll multiply by, just our little conversion fraction. We want to put pi in the bottom this time. This is converting from radians to degrees. And this one you can actually work out to be an exact answer, because the pi is the number that's creating the weird decimal here, right? The pi cancels out here. So I've just got -3/2 times 180, which of course is -270 degrees. So those were the first two, just straight up radian conversion to degree conversion. Okay. They'll just speak up if you want me to explain a little bit more about any of these problems. All right, so number 3 says to find the exact values of the 6 trig ratios of the angle theta in the triangle. Okay, so number 3, we've got a triangle. Let me get it there's the right angle. And where's theta? Theta's down here. And then we've got side lengths 205 and 200. All right, first thing I see is that this side is missing. So I can go ahead and use the Pythagorean theorem. I know that this side is my hypotenuse, right? Because it's across from the 90-degree angle. So it's going to be 205 squared is equal to 200 squared plus missing side I'll call b squared. B ends up being 45. Okay, so I'm going to call that 45 now. And now I need to write down every single trig ratio, or rather, well, yeah, the trig ratios for each of the 6 functions. So sine of theta, cosine of theta. And this is coming straight from their definition inside of a right triangle. Sine of an angle inside a right triangle, the sine of the angle gives a ratio of opposite over hypotenuse. Which side is relative to theta, which side is opposite? The 200, right? And 205 is the hypotenuse. And of course, this can reduce 200 over 205 reduces to, you pull a 5 out of both, leaving you with 40 over 41. Okay. Cosine of theta is going to be adjacent relative to theta. Cosine, right, is adjacent over hypotenuse. So 45 over 205. Again, you can pull a 5 out and you get 9 over 41. Okay, and this is what you would do for each trig function. So I'm not going to go through all of them, but tangent of theta would be opposite over adjacent. Secant of theta, remember, is so let me get it right. Hypotenuse over adjacent. It's the reciprocal of cosine, right? And then, so just in case, this would be hypotenuse over adjacent. Cosecant would be hypotenuse over opposite, right? The reciprocal of sine. So once you have the first three, it's really just a matter of flipping them over. So like if I know that tangent's going to end up being, if it's opposite over adjacent, what would that be? 40 over 9? 40 over 9, right? Yes. And then all I need to do for secant is flip cosine, so that would be 41 over 9. All I need to do for cosecant is flip sine, which is 41 over 40. And then all I need to do for cotangent is flip tangent. So there we go. That's how we do. And this is like one of those critical problems. Like this is, if there was like one problem to understand from exam 1, this is probably the main problem. So, okay, are we good so far? I hope I don't see any chats or anything popping up, so I'm going to keep going. Okay. Number four was a triangle, a right triangle again. We didn't get beyond right triangles, but that's okay. And it's a, if this is 90 and this is 45, then this must also be 45, right? So this is a 45, 45, 90. Do we absolutely need to recognize that to do this problem? No. What do we need to do though? We need to find, oh, by the way, but it's pretty obvious what we have to do, but I mean, find x is the official instructions here, right? Find x. Well, what do we know? We know theta. We know that, so we know theta, like the angle is 45 degrees. We know that x is the, how is relative to the angle theta, what is x? Well, it's not necessarily the adjacent side, even though it is adjacent to this angle, but since it's across from the 90-degree angle, that we know that this is the hypotenuse. This side over here would be considered the adjacent side, but that side's not going to come into play here. We also know that 40 is equal to the side opposite to theta. So remember, when you're given a right triangle and an angle inside, there are three sides relative to that angle. There's the opposite and adjacent and the hypotenuse. Okay, so now we're thinking, what trig function takes in an angle and spits out opposite and hypotenuse? Like what trig function gives us that ratio? You could say cosecant does, or also sine, right? Probably you would say sine because that's the one we're all more familiar with. Sine is equal to opposite over hypotenuse. Okay, why does that matter here? Well, because this tells me that sine of 45 degrees is equal to 40, the opposite side, over x. A little bit of algebra here says that x is equal to 40 over sine of 45 degrees. And then we know that sine of 45 degrees is square root of 2 over 2, right, from our reference triangles. So this is going to be x is equal to 40 divided by square root of 2 is the same as, I'm sorry, divided by square root of 2 over 2 is the same as multiplying by 2 over square root of 2. Okay. Am I losing you on the algebra? Let me go make sure. I've got the WebAssign open, so I don't have Teams open. Okay. Hopefully we're all good with that. Okay. And now finally, can we see if I write down here? Yes, right here. x is going to be equal to, well, I can clean this up and I can, in fact, go ahead and rationalize this denominator by multiplying by square root of 2 over 2. Long story short, it seems a little weird, but what ends up happening is you end up with 40 times square root of 2. Just because of the nature of what happens when you rationalize the denominators here, square root of 2 times square root of 2 in the bottom just yields a 2. So that ends up canceling with that 2. So this piece and these three pieces end up just canceling each other out, and you just end up with an extra square root of 2. And that attaches itself to the 40. So there we go. Okay, that's an important one too. So any questions? Okay. Number 5 is finding reference angles. I'm not going to do all of them because there's 3 parts. I'll just do like I'll do part C for me, which is negative 105 degrees. So remember to find a reference angle. First of all, a reference angle is made, it's an acute angle that shares a terminal side with this angle and goes to the x-axis. So its initial side is on the x-axis. Okay, so negative 105 degrees. This is negative 9, so I'm going this way, right? Negative 105 degrees would be like over here somewhere. That's that angle. So my reference angle, which I'll try to draw purple here, would be right here. I need to go from the terminal side of this angle, which is represented with a line here, to the x-axis, So it would be, now at this point you have to look at the geometry of what's going on and decide what angle has to be, like, quote unquote added here to complete a full revolution. Long story short, you're going to end up with your reference angle being 75 degrees. They're acute angles, and they should always be positive. So 75, because to go all the way, well, not all the way around, but to go from here to here would be 180, right? Would be 180. So what angle has to be here to complete that? It must be 75. And it is positive. They should always be positive. The point is, reference angles, when you write them down, they should always end up, if you drew it, it should always be in the first quadrant. Like in my picture here, it's not in the first quadrant. This is how I had to find it. But if I then took this angle and drew this angle, my reference angle, it's a tiny little positive acute angle. Well, the point is, it's in the first quadrant, right? It's positive and it's less than 90. Okay, so I'm not going to do all those. Number 6 was the same thing, except the angles were given in radians. I can do one of those. So number 6, I'll just do B. Was, for me, it's 11 pi over 9. Your numbers may have been a little different. It's because Lebesgue's going to randomize. Okay. First thing I should do is draw this angle. So I know that, how do you draw this angle? Well, you gotta know fractions, right? You gotta understand that 11 pi over 9 is the same as having a whole pi plus 2 little extra bits, right? Because this is 9 pi over 9, right? 9 pi over 9 plus 2 pi over 9 is 11 pi over 9. It's an 11. Okay. Why is this helpful? Well, this tells me that my angle is at least past this straight line, because I know this a straight angle in terms of radians is just pi. So there's pi, that's that part. And then a little bit further, and if I really wanted to, really wanted a good idea of where this is, I could even convert this little part to degrees if I really wanted to, by changing it like this to degrees, which would end up being, I believe 40. Is that right? I think that's right. Let's see. Yes. So it's 40 degrees past down here, so somewhere like there. So there's my 11 pi over 9. And then, so all this was just to figure out where the original angle is. Now I think, okay, reference angle should share a terminal side with the given angle. So it should be, this is its terminal side, and its initial side should be on the x-axis. So there it is. And now I need to figure out from the geometry of this picture, how do I discover this purple angle here? Well, I've kind of already done it, right? I've kind of already done it. It's the 40-degree part. It's the part that kept going here. So it's the 40-degree part. But of course, I want that in radians, right? Because they say, well, actually, yeah, if they give it in radians, then your reference angle should be in radians. So you would convert 40 degrees back to radians. But we kind of already did that here, right? It's the 2 pi over 9. So remember that finding reference angles, there's different things going on depending on what quadrant your original angle is in, and also whether it's positive or negative, right? Because like the last one I did, my angle was in this quadrant, right? The previous one I did, but it was negative. So my math looked a little bit different, right? So you don't want to try and like memorize what happens for each quadrant, for each type of angle, and then on top of that, memorize what you have to do for like radians. It's better to just draw the angle, get back to the x-axis, and use the geometry of what's going on to figure out what that angle is that gets you back to the x-axis. All right. Number 7. Okay, straight up, find the exact value of the trig function cotangent cotangent of negative 300 degrees. Okay, first thing I'm going to do is find the reference angle. This angle is negative 300 degrees. Let's see. So that's negative 90, negative 180, negative 270. Negative 300 is going to put me all the way right here. That's the negative 300 degree angle. So my my reference angle goes from the terminal side of this angle back to the x-axis. And how big is that? By the geometry of what's going on here, I know it's 60 degrees because 360 all the way around, right? So this must be 60 degrees. Okay. Sorry, 1 second. Okay. All right, cotangent then of 60 degrees is what I'm dealing with. I know that 60-degree triangle looks like this. It's 60, obviously drawing up my reference triangle now with this reference angle. And I know that that's going to be 1 square root of 3 and 2. Okay. All right, so I'm looking at cotangent, which is going to be cotangent of theta. Like, what's the ratio it gives? Well, it's the reciprocal of tangent, so it's got to be adjacent over opposite. So looking here, if this is the angle, adjacent over opposite. So for cotangent of 60 degrees, I'm getting 1 over square root of 3. And then I have to stop and say, okay, wait. Do I need to add a negative to this? Well, in the first quadrant, which is where, so do I need to add a negative to this? You look at where did your actual angle end up? Like not the reference angle, but this actual angle that you drew, it ended up in the first quadrant. Does cotangent yield a positive or a negative in the first quadrant? Well, it's definitely positive, right? Everything is positive. All the trig functions are positive over here, right? Cotangent would be negative where tangent's negative, and tangent would be negative in quadrant 2 and quadrant 4. Tangent is positive in 1 and 3. Hence, cotangent's going to be positive in 1 and 3. Hence, this is the answer. and 1 over square root of 3. There we go. You could rationalize that. I'm not worried about that. And WebAssign would take this as an appropriate solution too, but you could definitely rationalize that if you wanted to. Okay, the next one is very similar, just in radians, so I'll skip that. Number 9 was just straight up calculator problem, like just plug in sine inverse of 0.8. For me, it's 0.8. So you just literally plug that into the calculator. Make sure your calculator's in radian mode. I'll do number 10. So we've got a right triangle. Okay, we want to find theta in degrees. Rounded to 1 decimal place. In other words, to the 10th place. If you rounded wrong, I went back through the exams and gave partial credit. I already told y'all I would do that in case you forgot, because it was like 5 days ago. I went through everyone's exam and gave partial credit for rounding errors or stuff like that. Okay, so find theta in degrees rounded to 1 decimal. So we've got theta. What 2 sides do we have? We have relative to theta, we have adjacent is 20 and opposite is 9. Relative to theta, what's the angle, or rather, what's the side length next to theta? Not the hypotenuse, right? This is the hypotenuse. We don't even care about that here because this is going to be enough for us to answer this question. What trig function involves adjacent and opposite? Well, tangent, right? We know that tangent of theta, also cotangent, right? But we're all more comfortable with tangent. Tangent of theta is going to be 9 over 20, opposite over adjacent. Okay, now I'm going to use my inverse trig function on both sides. So what am I doing here? I'm taking the inverse of tangent on both sides. And I didn't leave room here to do it, but it would inverse tangent. So tangent with a little exponent of -1. Inverse tangent on both sides. Cancels here, right? Tangent inverse of tangent just yields whatever the input was, which is theta. And over here, I'm going to have tangent inverse of 9 over 20. Now, if the problem asked for an exact answer, then we would expect this to be some kind of ratio that we recognize, like square root of 2 over 2, or 1 over square root of 3, or 1/2. Some of those fractions that we're getting used to seeing that that yield angles like our 45, 30, or 60-degree angles, right? This is not, right? We do not recognize this as a common ratio that we're familiar with. Plus, the problem says round to 1 decimal. That's implying that we're going to be punching this into the calculator and approximating. So when you do that, make sure your calculator's in degree mode. You're just going to say tangent inverse of 9 over 20, just like that, and you'll end up with 24.3 degrees. No, 2. There we go, 24.2 degrees when you round. If you round right, you get 24.2. Okay. All right, any questions about any of those problems? Okay. I would like to go to chapter 6 then. Oh, by the way, I mean, should I even say this? I don't know. If y'all did the review, then none of the problems on the exam were, They were literally the problems from the review that I gave. With different numbers, obviously. Now, I'm getting on my phone because I left my notes for chapter 6, 6.1, my lecture notes at home today because I left in a whirlwind today because I woke up late. So I had to get my girlfriend to send me pictures of my notes. So I'm going to be working from my phone. Hope y'all don't think that's too unprofessional. All right, so chapter 6 is entitled The Unit Circle Approach. All right, what is going on? Here's the thing. The mechanics for everything that we're going to be doing in this section, you're already going to be familiar with. In fact, you're going to think that I'm just redoing a lot of stuff with literally like different letter names. Like instead of theta, I'm going to be using a T for angle. And you're not wrong. That's true. But there's kind of a greater point here that I'm going to try to make. So I'm going to go on a little bit of and get on a soapbox for a little bit. But we will get to some math today, and you'll see that the mechanics of everything we're going to be doing are going to be the same. Okay. So here's the big thing that we're going to be considering. We're going to be considering the trig functions of angles, so versus functions of real numbers. Okay, so instead of thinking of these trig functions as just functions of angles that output ratios of a side of a right triangle, we're going to be extending to functions, we're expanding the idea to functions of real numbers. And why does that matter? Why does that matter at all? Well, because it's going to allow us to look, well, the punchline is we're going to be looking at graphs of trig functions graphed on a number line, on a real number line. We're not just going to be considering, oh, look, these trig functions, they can do this cool stuff with right triangles, and, you can find missing sides of right triangles and stuff like that. We're going to be taking it up a notch and looking at them as functions of real numbers. So looking at every input on the real number line. And we'll see at the end of this chapter, it's kind of going to culminate in some pretty cool looking graphs that you've probably seen. You've probably seen sine and cosine graphs before. But that's I'm going to try to kind of set the stage for this. Okay. So just as a real quick review, in chapter 5, what did we do? In chapter 5, sorry. Zoom in. Oh, can I not zoom? Okay. We considered trig functions that took in angles. I'll say an angle took in an angle theta and outputted. So input is an angle theta, outputted ratios to, a ratio that took in an angle theta and outputted a ratio of two sides of a right triangle. That's kind of like, if I had to sum up all of what we've done so far, that's kind of it, right? We also said that we moved beyond acute angles, right? Because when you're talking about a right triangle, it really only makes sense if you're talking about acute angles, right? For it to still be a triangle. But we were able to move beyond acute angles by using reference angles. which is exactly what I did in that problem where it said, like, what is cotangent of negative 300 degrees? Negative 300 degrees is not an acute angle, but we can still complete that problem by this idea of reference angles and reference triangles. Okay. Now, what else did we see in chapter 5? We saw that for an angle theta on the coordinate plane, we can write a corresponding, oh, what did I say here? Hang on, sorry. Yeah, that's fine. We can write a corresponding coordinate point. Let's say coordinate point. This is informal, but that's okay. Coordinate point. Okay, I'm going to draw a picture of that here. The picture, we've already seen this picture, but I'm just kind of reiterating here. So if we have some angle, let's say some angle theta, then we can, for a given length here, which we'll call r, we can consider this coordinate point, which, by the way, would come from the x value is how long this side of the triangle is, if I drew a right triangle here, and this side is the y value, how long this leg of the triangle is. So we found this way to get back and forth, and it's really just the right triangle trig stuff again, right? We found this way, though, that we could get back and forth between an angle, theta, and coordinate points, but we really didn't talk about it that much. I kind of drew this picture, and I said, look, x is going to be equal to r cosine theta, y is going to be equal to r sine. This is just coming straight from the trig ratios. Sine of theta is equal to opposite over hypotenuse, right? Y over r, and then just multiplying by r on both sides to get this. And what else can we say from this right triangle? We can build some nice formulas. We can say the hypotenuse is just going to be, so we've already seen this. And by the way, theta would be tangent inverse of y over x. This way of getting from an angle and some given length of a line here, r, I'm just saying, just kind of being vague about it, to get back and forth between those values and xy coordinate points. And that's kind of where we left that in chapter 5. Didn't say too much more about it. We're going to explore this a bit more. Okay. Okay, so now we will push this picture further. What do I mean by that? What do I mean by we'll push this picture further? We will consider the trig functions with inputs that are real numbers. Okay. So we'll consider the trig functions with inputs that are real numbers instead of angles. This will allow us to create graphs of our functions. Okay, so hang on. What is going on? Our trig functions, right? So, okay, what is going on? I'm saying that once we make the conscious decision to move from just considering the input of our trig function as an angle to just some generic real number, we're moving to a place where now we can literally graph the whole trig function. Like because I should say on a graph, right? This is the real number line. They're both real number lines, right? These are both real number lines. So if I'm inputting just some generic real number into a function, then I should be able to graph it, right? I should be able to graph it. Okay, so that's kind of the big idea here is that we're going to be plugging in generic real numbers and getting into our trig functions and getting values that we can plot on the coordinate plane. Okay. Now, I said the mechanics are going to be the same. Let me say a little bit about that. In sections 6.1 and 6.2, everything is pretty much going to look the same. So we're going to be setting the stage in these two sections. Everything is going to look the same, except that theta, which is an angle, will be replaced by a real number, t. We're not using, typically you would use x, right, for your input of your function to represent just a generic real number, but we're not going to use x because of the way we're going to graph these things. We're going to want to talk about x. It's going to be better to use just some other variable here, so we're going to use t. Okay. So really, as we go, I haven't even started 6.1 yet. This is still like chapter introduction. What's going to be happening, if you're not paying real close attention, it's really going to look all the same. Like it really is. But there's some details, there's subtle things going on in the background that are going to allow us to do some new things, namely graphing the trig functions. Okay, so I think I've said enough about that. Let's actually get into 6.1, this whole unit circle thing. We got to talk about that. So we got to talk about because the name of this chapter is the unit circle approach, so I need to explain what the unit circle is and everything. First of all, just recall the definition of a circle. Okay. X minus h all squared plus y minus k all squared is equal to r squared, where h comma k is the center and r is the radius. Okay, the unit circle is a special circle, a very specific circle. The unit circle has center 0, 0 and radius 1. So its equation then is going to be x squared plus y squared, so no minus h or minus k because the center is 0, and equals 1 squared, which is just 1. So there's the equation of the unit circle. Okay, and I'm going to talk about why we're even mentioning the circle. Okay. Let's just, so you're probably still like wondering like what the heck is going on? Why are we talking about a circle? Well, we'll get to that, but first let's just make sure we're comfortable with the math of circles. Let's just kind of remember that. So let's just do a couple quick examples with the actual unit circle here. Oh, goodness, this is... Okay, confirm that the point P equals square root of 3 over 2 comma negative 1/2 is on the unit circle. All right, so all we're doing right now, I'm not talking anymore about like why are we talking about a circle, right? And kind of putting a pin in that and just saying, before we get there, let's just make sure everyone's comfortable with the math of circles, right? Or at least this part of it. So if I want to confirm, oh, by the way, look at these coordinate points. It's no coincidence, you'll see later, it's no coincidence that these are some ratios we recognize, right? The square root of 3 over 2 and a negative 1 over 2, that should be making us think like, oh, that's like, those are like outputs for a 30, 60, 90 reference triangle. You know, maybe, I don't know what the, you know, maybe sine and cosine or something like that. But so we don't need to say any more about that, but just kind of recognize that those are on the unit circle. How do I confirm they're on the unit circle? I just plug in the points, or rather the point, and just confirm that I get equality. So I'll say x is square root of 3 over 2, so y is negative 1/2. So apparently when I square both of these and add them up, I should get 1. I should get 1. Oops. So square root of 3 squared is just going to be 3 over 4. Right? Square root of 3 squared is 3. 2 squared is 4. And then plus negative 1/2 squared is just going to be 1/4. So I get equality. 3/4 plus 1/4 is 4/4, which is 1. Okay, so easy enough, right? Just make sure your algebra is fine there. That's how you confirm that a point is on the unit circle. Here's a more interesting example, but kind of in the same vein here. Example 2. The point Q, let's call it Q, so we have a different name. The point Q equals negative square root of 2 over 2 comma y is on the unit circle. And what am I going to ask? I'm going to say solve for y. Okay. Okay, I'm going to get rid of this. Okay, so hopefully you're kind of thinking like you're already maybe working on this. We're going to start off with the unit circle equation here. I'm being told that a particular x value is there, negative square root of 2 over 2 all squared. And I'm being asked to find the y coordinate of this point. So clearly I'm going to solve this for y, right? I'm going to solve this equation. That's a 1. Solve this equation for y. So what will I do? I'll square this, so the negative gets absorbed. So I have square root of 2 squared is 2 over 4 plus y squared is equal to 1. I'll subtract 1/2 from both sides because that's just 1/2, right? So I'll subtract it over. I'm getting y squared is equal to 1/2. And then y is going to be equal to plus or minus square root of 1/2, taking the square root on both sides and not forgetting the plus or minus. Now here's where we run into a problem, because I've got two potential values. And by the way, if we rationalize the denominator, this would end up being square root of 2/2. So you can just make a little note here to yourself and say we rationalized denominator. Square root of 1 is just 1 over square root of 2, and then you'd multiply by square root of 2 in the top and bottom. You'd get this. But the point is the plus or minus is still there. And that's a problem. I was asked to solve for y. I need one value for y. So what other info must I be given in this problem? And if you look at this problem in the text, they'll say, assume that, that Q is in, so the point Q is in quadrant 3. So what does that mean for my y value down here? In quadrant 3, x and y are negative, which checks out with Q having a negative x value, so that means my y value must be negative square root of 2/2. It matches the x value. By the way, both of these coordinate points, negative square root of 2/2 and negative square root of 2/2, they're looking familiar again, right? These are like some ratios we're used to seeing from our trig functions. Okay. Okay. We good with that? This is kind of nice, right? This is like 112 stuff. It's like not really any trig going on for real. It's just solving equations. Okay. Oh, where's my phone? Okay. Y'all just let me know if there's any questions. I'm doing a lot of the algebra. I'm brushing a lot of the algebra under the table. So just let me know if you actually want to see any of those. It's no problem. All right. Here we go. Here's where we're really going to get some details that hopefully make this transition from theta to t, from angle to real numbers, make a little bit more sense. Okay. Yeah. Let t be a real number that describes a distance along the unit circle, a distance So here I'm going to be getting to why the heck we're talking about a unit circle in trig. Along the unit circle. So t is going to be a distance that's traveled along the unit circle with initial points. Well, how am I saying? Yeah, that's fine. Initial point. Where would we consider the starting point? Well, it's going to be on the positive x-axis. That's where we're always starting stuff like angles and whatnot. So along the unit circle with initial point on the x-axis. And since it's on the unit circle, I can say exactly where it is. What is the point that's on the positive x-axis? Positive x-axis. If I draw the unit circle, centered at 0 with radius 1, so it's hitting all these 4 points at this point is 1, 0, this point is 0, 1, this point is -1, comma 0, and this point is 0, comma -1. So here's my circle. Wow, that is ugly. Wow, that's super ugly. But anyways, that's a circle with radius 1 and center 0, 0. So that's 0, 0 there. So, okay, where is the point on the positive x-axis that t is going to start at? Well, it's at the point 1, comma 0. So specifically the initial point on the positive x-axis at 1, comma 0. Okay, what else do I say? So what does this mean? What is t then? Let me draw you a better picture. Give you a better picture here. In fact, I'm going to make it bigger. Okay. Okay, and I'm going to draw the circle. Dotted points there. I'm going to draw the circles with a dotted line. So I can draw my t on here too, because I'm going to be drawing t on this picture. So here's the point 1, comma 0, 0, comma 1. Okay, so t is a distance along the unit circle with initial point on the positive x-axis. Ooh, I'll use purple for t. So t starts here and travels some length like this, and that's t. T is that distance. T is the distance along a circle. What do we call that? What do we call the distance, a piece of a distance along a circle? So t is an arc length. Right, that's the technical name for a piece of a circle like that. Just the piece of the outside of the circle. The entire thing we would call circumference, but if it's just a piece, it's called an arc length, the length of an arc. But what the heck is going on? But t was supposed to be an angle, right? I told you that theta is going to be replaced by t. T was supposed to be an angle. Oops, an angle. So why? Okay, that's a good question. But if we recall, now here comes the whole point of the unit circle here. Consider that arc length, remember from earlier, we very briefly talked about this, arc length is equal to radius times the angle described by that arc, right? Like if you want the length of this arc, you got to know the radius of the circle and also how big the angle is described by that arc. But what is our radius? If t is traveling along not just any circle, but specifically the unit circle, then what is the radius? But our radius is 1 because we are on the unit circle. So arc length, the formula boils down to, if radius is 1, is equal to angle. Oh, in radians, of course. This is angle is in radians. Okay, arc length is equal to the angle here in radians. Okay, so I'm kind of building up t here. So I'm basically explaining that t is an angle, right? T is an angle. It has to be, for it to be an arc length as well, which is what we're going to want, we need to be talking about the unit circle, t being specifically a value that measures distance of an arc along the unit circle. Okay, now here's some just basic facts here. Okay, if t is greater than 0, we measure counterclockwise. So that's counterclockwise, CCW counterclockwise. Same as with an angle, right? So this t I drew here would be positive. If t is negative, we measure clockwise. So, okay, nothing new there. That's how we dealt with angles too, right? If they go this way, they're positive. If they go that way, they're negative. Okay. What else can I say? I need to erase this. I'm trying to erase so that you have in order so that you have time to write everything down. Or maybe you're just listening and you'll take notes on the recording later. That wouldn't be a bad idea. Now, let's say that since t is a distance, t ends at some point. So it begins at some point, well, specifically 1, 0, ends at some point, like if I drew it here, I'll name the point P, which is a coordinate point, right? It ends at some coordinate point, which the way we like to notate that is like P of xy, kind of like P of xy. That just means the point at xy on the unit circle. It's still on the unit circle, right? On the unit circle. So here's the big idea. Here's what we're going to be doing in section 6.1. We will be solving the problem of given t, find P of xy. Find the coordinate point. So if I tell you that t is equal to pi, that means it goes all the way around and ends here. What coordinate point does it end at? Okay, we're going to be answering questions like that. Okay. How much time do we have? Yes, good. We're doing good on time. Here we go. That is enough setting the stage. It's time to do some actual problems. I'm going to give you a second to write that down. And we'll actually do some practice with this. Given t, find that point that it ends at. All right, example 3. Find the point P of xy for each value of t. For each value. I'm going to write them all down over here, just so I don't have to keep opening my phone. Just give me 1 second. Okay. Okay, I won't have to keep opening this, at least for this example. All right, so we're going to find the terminal point that t ends at for each value of t that I give here. So I'm looking for a coordinate point. All right, so if I draw this, I'm going to draw this t value on my unit circle, Okay, if the length is 0, so remember, t is going to be some arc length, but if length is 0, then I don't go anywhere, right? And remember that initial point is 1, 0. Oop. Sorry, 1 second. Somebody got, okay. All right, so if t is equal to 0, then the arc length is 0, right? It didn't go anywhere, so it stayed at that original point. So for t equals 0, p of xy is equal to 1, 0. It stayed right at that point, 1, 0. By the way, well, yeah, I'm gonna say that I'm gonna kind of give it all away here. We already know how to do this with our trig functions. We can say, in general, p of xy, now this is on the unit circle, okay? P of xy, so, well, I should say in general, but really not complete generality, so let's say on unit circle, which we're going to be dealing with the unit circle for the next few days, so P of xy is a coordinate point, right? Is equal to cosine of the value t, comma, sine of the value t. That's kind of giving it away. This is kind of like what we're building up to today, but whatever, there it is. Does that check out here? Well, what's cosine of 0? Cosine of 0 is 1, right? What's sine of 0? Sine of 0 is 0. So this checks out. This works. This is just coming straight from that picture I drew. That picture I drew with the triangle with, so where's this coming from? Let me redraw the picture. Oh, dang it. No, there we go, that's fine. The picture, so here's t. This is t, that curve there. This side length is x, this side length is y. That coordinate point then is p of xy, right? That coordinate point there, right there. And what is the radius? If we're on the unit circle, t is measured across the distance on the unit circle, so the radius is 1. What is the angle? Does anyone want to say? I haven't gotten you guys involved here, so does anyone want to venture a guess as to what the angle is? On the unit circle, arc length is t. What is the angle? It's t, right? It's t. Sorry if I didn't give you enough time to answer, but it's t, right? Because remember, this is a special case on the unit circle where the angle measured in radians is the same as the length of its arc there. Okay, so what does that mean for this point right here, this coordinate point here? What is the y value going to be? Well, I know that, for instance, cosine of t is going to be equal to adjacent over hypotenuse, but hypotenuse is 1, so that's just x. So that means the x value of this coordinate point is cosine t. Sine of t is equal to the opposite side over hypotenuse, which is y over 1, which is just y. So this coordinate point is an xy point, and its inputs are cosine t and sine t. This is a special case of that, where we didn't really create an angle because t is just 0. So this is kind of a special case. You wouldn't go through all this stuff to get this answer, because if you know t is starting at 1, 0 and its measure is 0, it's not going anywhere, so it just stayed at the same place. But I'll keep that picture up there, and we'll see if that helps with any of these. These are kind of some weird angles though, so maybe this picture won't help as much. This picture is more like the general idea. Everything I'm working on in this example 3, these are kind of all special angles. So it's not that this picture doesn't make sense, it's that you wouldn't really use this method to solve these problems. Okay, so if t is equal to pi over 2, where is that putting t? From here at 1 comma 0, right there, right? That's pi on 2. But what's that coordinate point? On the unit circle, remember, you got to remember the setting is the unit circle. On the unit circle here, that point is 0 comma 1. So that means for this value t, pi on 2, the point xy is equal to 0 comma 1. And you could really hammer that home by saying, okay, well, if I'm not convinced, what is cosine of pi on 2? Well, it's 0. What is sine at pi on 2? Well, it's 1. Okay. That's coming from those tables that we looked at a while ago. So if you're not remembering those like special values like sine and cosine, what their values are on each axis, you'll want to go back and look at those tables from chapter 5. I'm sure they rewrite them somewhere in chapter 6 too. Okay, so there's that one. How about part C? T is equal to pi. Okay, T, so this is what you should say to yourself when you write this down. T is the measure of an arc length along the unit circle. So I'm thinking of, okay, starting here, if I'm on the unit circle and it's starting here, that's the point 1 comma 0. And I need to measure an arc length of pi, right? An arc length of pi, but I know that's going to be half of the, oh, that's nice, look at that. Half of the circle, right? Well, half of its total arc length, right? Total arc length would just be 2 pi, because its radius is 1, right? So it would just be 2 pi all the way around, but I'm only going halfway, so that's just pi. And now I say, what coordinate point is that on the unit circle? It is negative 1 comma 0. So for this t value, p of xy is equal to negative 1 comma 0. Okay, I'm going to go ahead and erase. What does that C? Okay, D is 3 pi on 2. Again, I'm thinking this is an arc length along the unit circle. I already know that from here, which is 0 comma 1, that's where I'm starting. This is pi on 2. This is a full pi. If I want to go to 3 pi on 2, then I know I should go here. And all I have to do is say, what is that coordinate point? So again, this picture over here that I drew is not really coming into play here. It will very much later once we can. This is a long example, just kind of reiterating all these like special angles on the axes. What is this coordinate point down here? It's 0 comma negative 1. So p of xy for this t value for this arc length slash angle is 0 comma negative 1. Okay, now E, I'm going to do E, and then I'm going to give you a chart because I said the chart's in the book, but I'm just going to reiterate these special angles, and then I'll leave you with F, G, and H to do for exercise. All right, T is equal to 2 pi for part B. All right, thinking this is arc length along the unit circle, but the unit circle, remember, its radius is 1. So this is the entire circumference, right? This is the entire circumference. It goes from right here, here's pi on 2, here's a whole pi, 3 pi on 2, all the way back. Look at that, that's a good, no, it's not, that's pretty ugly. It looks good from over here. Okay, anyways, this is where it ends. It goes all the way, and it ends right there again. That's a full 2 pi arc length on the unit circle where the radius is 1. So that means that p of xy just ends up back at 0 comma 1. So we're seeing that same behavior we saw in chapter 5, where two different t values can yield the same coordinate point. And that's fine. That's what happens with these trig functions. They're cyclic, they're repetitive, right? Like for instance, the very first one we did, t equals 0, gave the exact same coordinate point. And every single thing that ends at that point, so 0, 2 pi, 4 pi, 6 pi, 8 pi, even whole numbers of pi, will all, their terminal point would all be 0, 1. All right. Here are the values. Here's a table to write down for some special angles, all the 5 special angles we just looked at. And when I say angles, I'm talking about t, right? T is an arc length and an angle in this setting. All right, so sine of t. Oh, no. Let me say cosine. We'll do it in order here. Cosine of t, sine of t, and then the coordinate point corresponding, p of x, y. Okay, 0. So I'm writing down all the half pi. 0, pi on 2, pi, 3 pi on 2, and 2 pi. All right, here we go. Cosine at 0 is 1. Cosine at pi on 2 is 0. Cosine at pi is -1. 3 pi on 2 is 0 again, and then back to 2 pi. That's the one where we should see repetition, right? And we do. It's back at 1. So it goes 1, 0, -1, 1. So it's going 1, 0, -1, 1. We're going to see that reflected in the graph later when we actually graph these. Sine is like the opposite. At 0, it's 0. At pi on 2, it's 1. It's like shifted, right? The pattern is shifted. At pi, it's 0. At 3 pi on 2, it's -1. And at 2 pi, it's 0 again. See how it's shifted? It's like if this was a big row of numbers that I could move up and down, I could just take this and I could take this one and shift it down by 1 and I would get this column, right? They're very similar. Sine and cosine are just, later we'll have fancy terminology to describe what it is, how to describe this relationship. But for now, I'll just say they're very slightly shifted, right? And if I just shift one of them, they would be matching. If I shifted one of them slightly, by pi on 2, in fact, they would be matching. Okay, now what's the coordinate point corresponding? Well, it's just xy, 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 xy. So it's 1, 0, 0, 1, -1, 0, 0, -1, and then back around to 1, 0. This sums up a lot right here, right? This sums up pretty much the entire example. But let me give you 3 more little parts here to try on your own, f, g, and h. F is t equals 3 pi. So that would be all the way back around. Whoops. G is t equals -pi. So this one goes the opposite direction. Okay. And h is negative t equals -pi on 2. So that one goes clockwise as well. And it'll be one of these 4 coordinate points. I'm saying only 4 coordinate points because this one is a repetition of this one. So out of these 4, each of these will be one of these 4 coordinate points. All right. So before we still have 15 minutes, but let me see. That's probably it for today. So next time we're going to look at the angles in between these, namely the ones we're comfortable with, the pi on 4, pi on 6, pi on 3. We'll make a new table. We're going to see a lot of those ratios coming again, the square root of 2 over 2, square root of 3 over 2, 1/2, and the negatives of each. Yeah, we'll do some practice with that. We'll talk about the idea of reference angle is going to translate over here. We're going to call it a reference number for t. we'll talk about that. Yep, that'll be 6.1. So we'll finish 6.1 probably in like 30 minutes next class, but I'll leave it here, even though we have 15 minutes. So you guys are good to go. You can stick around if you have questions. I'm going to stop the recording.